Okay, so we start here. So today we'll try to finish because already 17 minutes has gone in this spamming, right? So we'll try to finish this slightly faster, right? So the first topic we will be discussing about the velocity potential function. As I said that it is a scalar function of space and time such that its derivative with respect to any direction will give you the direction of resultant, velocity component in that direction. All right, so definition is simple. It is a scalar function of space and time such that its derivative with respect to any direction gives the fluid velocity in that direction. So usually we represent this by this coordinate system. So where you can see along x direction we are having velocity component u. All right, along y direction we have v, and along z direction we have w. All right, so we can write here. Here W. So this is not W in this direction. We are having only U in this direction. So as per this definition, we say that we can write U is equal to dou phi divided by dou x, and we can write small v is equal to dou phi divided by dou y. We can write small w is equal to dou phi divided by dou z. So these are all velocity components along x, y, and z direction. Now, what is the must condition for the flow? I mentioned earlier, must condition is that if I am saying certain flow is existing, that means that flow must satisfy the continuity equation. If any flow which is not satisfying the continuity equation is not possible in reality, that you keep in mind. So, as we are considering all x, y, z, that is the three-dimensional flow field, and for three-dimensional flow field, we know the continuity equation, right, in terms of x, y, z coordinate. So, can any one of you tell me what is the continuity equation in terms of Cartesian coordinates? Yes, any one of you? For a three-dimensional flow, what is the form of continuity equation in terms of x, y, z? Yes, are you there?
Sir, dou u by dou x into dx
Yes. Next.
plus dou u by dou y into dy plus dou u by dou z into dz equal to 0, sir.
That means what? That means it is in the case of, what is the case? Condition you tell me. Condition is steady flow,
Steady
because
flow, yes.
otherwise next term will also come, right? So so as we are saying that u is equal to dou phi by dou x, and v is equal to dou phi by dou y, right? This is phi, and w is equal to dou phi divided by dou z. If this is the case, then what we can do is continuity equation that we need to write. Continuity equation for three-dimensional steady steady flow condition, we can say that dou u divided by dou x, dou v divided by dou y, plus dou w divided by dou z must be equal to 0. If this is not getting satisfied, in that case we will say that such kind of flow is not possible. So now substitute the value of u, v, w in these terms. The moment you put the value of u, v, w here, you can say dou square phi divided by dou x square plus dou square phi divided by dou y square plus dou square phi divided by dou z square. This should be equal to 0. Right? You are getting this equation. And this equation is basically known as Laplace equation on phi. So we can say that the velocity potential function will only be existing, right, if it is satisfying the Laplace equation on phi, right? So this is the necessary condition. So any possible flow must satisfy the Laplace equation on phi. If it is not satisfying this, we will say such kind of velocity potential function is not existing. This is the one property. Now we will see the next property. Next property talks about the rotationality, right? Rotationality. So when we are talking about rotationality, we have defined the rotating type of flow or rotational flow. Rotational flow is such kind of flow in which all the fluid particles of the flow domain will rotate about its own mass center. When such kind of phenomena is happening, we say that rotational flow. If they are not rotating, they are simply moving from one point to another point. We will say that such kind of flow is called a rotational flow. Right. So we have to check for rotationality, and for rotationality, usually we check by the term called rotational components. Derivation is not there in your syllabus, but I will give you some formula. So in order to find out the rotationality, you can use this formula, right? That says dou w divided by dou y minus dou v divided by dou z. So this is for x. Similarly, you can write for y. When you're writing for y, you can write in this way. So dou z, here you write dou x. Whatever term is here, that will come here, dou u, and here dou w. Right. Similarly, we can write for z, rotation about z axis. Contributor will be basically x and y here, right? So in between minus, and you can write here v, and here you can write w. So net rotation, when we are writing in this way: wxi, wyz, and wzk. This is called net rotation when we're talking about rotationality. Now, substitute the value of UVW in this. Take any one of this, right? You will get an idea. We will take only WX. So half, put the value of W. W is dou phi by dou Z. So we can write dou square phi divided by dou phi, dou Z. Second term you look at, this is again phi by Y. So we can say dou square phi by dou y, dou Z. So we are getting exactly equal to 0. Similarly, if you are going to put in all these, you will get Wy is equal to Wz also equal to 0. So we can say that net rotation is 0. So what we can say from here? From here we can say that potential flow is always an irrotational flow, right? So we can say from here potential flow is an irrotational flow. Is that clear? So, as a whole, if you are combining all these two statements, right, when we talk about continuity, so we can say if a velocity potential function is existing and it is a possible case of fluid flow, then it is a case of an irrotational flow. So, as a general statement, you can say if any flow satisfies the Laplace equation of phi, then it is a possible case of irrotational incompressible flow. Just note it down. If any flow satisfies Laplace equation on phi, it is a possible case of irrotational and incompressible flow. So velocity potential function actually exists only for irrotational flow. So we can write 2 points here. One point says that velocity potential function exists if it satisfies Laplace equation on phi, right? Second, if potential flow exists it is a case of irrotational, incompressible fluid flow. These are the two important observations. So here also you can say potential flow exists, right? Instead of this velocity potential function, right? You can write a potential flow exists, right? You can say that it is a case. So you can delete this entire statement up to here. Flow exists then if it satisfies the Laplace equation of phi. This is a mandatory condition, right? And this is the property of potential flow, right? That will always be an rotational flow. So this is the one thing. Next one is stream function. When we are talking about stream function, we can say that it is a scalar function of space and time such that its derivative with respect to any direction gives the fluid velocity at right angles to that direction. So if we are putting the derivation with respect to x, if we are deriving, we are saying dou phi by dou x. So dou phi by dou x will actually represent the velocity in y direction. So we can say v is equal to dou psi by dou x. If we are differentiating with respect to y, if we are saying dou psi by dou y, then it will give you the velocity component in x direction. That is called small u. Why it is coming like this? Because when we defined the streamline, right? What is the property of streamline? There is no cross flow across the streamline. No flow can cross the streamline, so it will always be following the streamline. So that means perpendicular to that, you will not get any kind of flow, any kind of flow. So that is a one of the property. So like stream function, if you are differentiated with respect to the x-axis, it will show the direction perpendicular to it. That means it will give you only the velocity component in y direction, that is represented by the small v. So as per this, when we are writing mathematically, we can say that u, when you are talking about u, this will be the partial derivative of psi with respect to y. So we can say dou psi divided by dou y. And v, this is small b, this is nothing but negative sign dou psi divided by dou x. So these are the velocity components, right, for the stream function. Now, once you say that the stream function exists, that means it must satisfy the continuity equation. So we can write from continuity equation. So just put the value dou u y dou x plus dou v y dou y is equal to 0, because it is will be applicable only for two-dimensional flow. There is no z direction. If you differentiate with respect to z direction, you will not get any kind of velocity component, because there is no cross flow across the streamlines. That's why we are getting only two velocity components, either u or v. There is no w. So stream function exists only for two-dimensional flow. Now substitute the value over here. The moment you substitute the value over here in the left hand side, you will get dou square psi divided by dou x dou y, and this side dou square psi divided by dou x dou y, which is exactly equal to 0, which is exactly equal to 0. So we can say that psi satisfies the continuity equation. So it is a possible case of fluid flow which may be irrotational or rotational, which may be rotational or irrotational. So you can say statement here, psi satisfies continuity equation, hence it is a possible case of fluid flow which may be rotational or irrotational. We don't know. But for potential function, velocity potential function, we directly say velocity potential function is existing, that means it is a possible case of an irrotational flow. But here we cannot say whether it's rotational or irrotational. We will see now. So from continuity equation, we saw that it is satisfying the continuity equation. Let's go for the rotationality now. So check for rotationality. Check for rotationality. So when you are checking for rotationality, I will take only one component. With that, I will get an idea. So I am taking WZ because it is applicable only for U and V component which we have seen in stream function. So only WZ will come to the picture. So here we can write dou V divided by dou X minus dou U divided by dou Y. Just substitute the value of U and V over here. So if you put the value here, this will become minus dou square psi divided by dou x square. This is also minus dou square psi divided by dou y square. So you are getting this term, right? That is in minus. Now, if it is an irrotational flow, if I say that it is an irrotational flow, then this Wz should be equal to 0. Clear or not? So if you are doing say, do that thing right, you will get only one equation dou square psi and dou square psi divided by dou y square is equal to 0. So this equation is known as Laplace equation on psi. So we can say that if set psi satisfies the Laplace equation, it is a possible case of a rotational flow, right? So you can say that here if psi satisfies Laplace equation, then it is a possible case of a rotational. Clear? So that means from these two statements, right? One is for velocity potential function, for stream function. Velocity potential function is somebody saying that velocity potential function is existing. That means it is a possible case of a rotational flow. There is no doubt. But in the case of stream function, if stream function is existing, that may be rotational or irrotational. It will only be irrotational if it is going to satisfies the Laplace equation on psi. This is the required condition. So any doubt in this?
No, sir.
So as a note you take, because this is very, very important in 2 marks questions, right? Even gate examination you may find this question. So note the first point is says that if stream function psi exists, if somebody is saying if it is existing, we can say it is a possible case of fluid flow which may be rotational or irrotational. Second point that we got from here is if stream function psi satisfies Laplace equation, then it will be a case of irrotational flow. Yeah, so these two important observations you have made from phi, and we have made two important observations based on phi, that if phi exists, that means it has to satisfy the Laplace equation on phi. Once we came to know it is existing, that means it is a case of a rotational flow. So potential flow is always a case of a rotational flow, but streamline flow may be rotational or arotational. That you keep in mind. So next topic, relationship between stream function and velocity potential function. How to relate? how can you relate interrelationship between these two, that we will be looking for. So for that, what we will see, we will go one by one. So first equation will write for the equipotential line. Take the equipotential line. So we can say it is a line along which velocity potential function remains constant, right? Remains constant. A line along which phi remains constant is known as equipotential line. So as we know that phi is a function of x, y, right? And you can consider z also, which is a constant, and we want to make a relationship between stream function and velocity potential function. So we need to consider only two-dimensional case because stream function exists only for two-dimensional case, that is x and y direction. So we need to consider only x, y in this case. Z can be neglected. So when you are writing very minute change in d phi, so its phi is constant, so d phi will be 0, right? Which is nothing but when you are writing d phi, we can write dou phi by dou x, right, into dx plus dou phi divided by dou y into dy. This we can write because we are considering only x and y. Z is not present. So what is this? This term is u, this term is v. So we can say d phi is equal to u dx v dy. Clear? And this is equal to 0. If you put this equal to 0, you can find out dy by dx, right? This is called slope, right? When phi is equal to constant is nothing but minus u divided by v. So this is the slope for equipotential line. You can say equation number 1. Next case, you consider the line along which psi is equal to 0, or you can say the line of constant psi. So second case is line of constant stream function, that is known as psi is equal to constant. So we can say psi is a function of x and y, same analogy use, which is a constant. So you can say d psi is equal to dou psi by divided by dou x tx plus dou psi divided by dou y dy, which is equal to 0. So we can say that from here dy by dx, that is the slope of psi is equal to constant. So just you substitute the value over here. So one more term is needed. So what is this? This is minus v dx. This is u dy is equal to 0. So from here you can say dy by dx is equal to v divided by u. This is your equation number 2. So multiplying 1 and 2, right? Multiplying 1 and 2, 1 into 2, right? We have, so as we are saying slope, so we can say m1, right? This is a slope. Usually we say by m1 into m2 is equal to, we can say this is u by v, this is minus u by v into v by u, that is becoming minus 1. So two slopes, right? If I say this as m2 and earlier one was m1, this I am saying as m1. So what is this important relation? M1 into M2 is equal to minus 1. That means equipotential lines and stream lines are orthogonal to each other. So we can say that phi and psi are orthogonal to each other. Clear? So if I draw the phi along x-axis, I will be drawing psi along the y-axis. Psi along the y-axis. Next one is flow net. So when we are saying about flow net, it is a grid of series of equipotential lines and stream lines of constant values, right? It is actually it will be something like that. It is a grid of series of equipotential lines and stream lines of constant values, right? So it will be forming a some sort of grid, like when you are doing any kind of analysis, either flow analysis or structure analysis. What you need to do? You do meshing. Meshing is called nothing but grid. You are creating the grids. So if you look at the one element of that grid will be a square element. And for the sake of simplicity, we always consider the square element for the study instead of going for circular element, because writing the quadratic equation and solving the quadratic equation is much complex than the solving the linear equation. So that's why we always consider the square elements everywhere. So like if I want to see in a pipe, if it is a pipe is something like this. This is a pipe which is undergoing in convergent portion. So here it is a constant almost. From here it is converging the area, and finally flow is coming out from this side. So we can say that this is the case of flow through converging boundary, right? Flow through converging boundary. If that is the case, and I want to analyze how things are happening in this, so what I need to do is I need to draw the flow pattern. So flow pattern, as I said, that there are two kind of flow pattern, right? That we consider. One is called streamline, which will give us the direction. First, I will draw the streamline. So streamline will follow the boundaries, right? It will be going like this. So streamline will show us the direction, right? So it will be going like this, right? Second streamline. Chances are middle line will be going exactly straight, right? Then from this side also flow will be going like this, right? So I'm considering. So these are all the line of, you can say, psi is equal to constant. So constant psi line. And now we need to draw the equipotential lines. As we know that equipotential lines are perpendicular to this. So we can draw from this boundary, right? Like this kind of lines it can be drawn. So these all lines, right, that you are getting is, these all lines are phi is equal to constant line. So look at the combination. So combination is basically helping us to see how your flow is behaving within this closed vicinity. It was a closed pipe, right? In which how your flow is going, we can easily see with the help of stream lines and equipotential lines. You see over here. And if I want to analyze the flow behavior, I can say starting from 1 point and going at a 2 point. I want to see the effect between this. I will consider any fluid element. I will consider only this one for our study. So I have considered this. Look at this. This is just a square. So I will apply what is entering, what is going out, and I will take the energy balance. Then I will integrate from 1 to 2. I will get the net effect. So like this, you can analyze any kind of flow behavior in any kind of flow geometry. It was the simple geometry. There may be complex geometry also, right? In that possibility is that we can easily identify the areas, right, where we need to do some modification to avoid any kind of resistance to the flow, right? That is usually we say drag or air resistance or water resistance. If you want to reduce, you can do some minor geometrical changes to the existing geometry, and you will get the effective flow distribution right in the pipe. So as this was the solid pipe, and within that we got all this flow phenomena, or we can say flow simulation. We can easily visualize the thing with the help of phi and psi line, constant phi and a constant psi line, and this complete setup is known as flow net. So we can say this as flow net. So flow net will be useful for analyzing the two-dimensional rotational flow, two-dimensional rotational flow. So any doubt in this?
No doubt, sir.
So this kind of questions, right, may be coming from this topic. So this is just what you today you understood, right? What is the velocity potential function? What is the stream function? The stream function is basically related to your streamline, concept. There you stated that there's no flow, there's no cross flow, right, across the streamline. So only possibility is that between two streamline, two-dimensional flow may be happening, not three-dimensional flow. But in the equipotential lines, right, as these are not showing the direction, so and here three-dimensional flow geometry is also possible. But in the case of two-dimensional case, or you can say streamline concept, only two-dimensional flow is possible. Either you can consider along x and y, or you can consider x and z, or whatever z and y. Only two-dimensional flow is possible to be analyzed with the help of streamline concept. So any kind of flow geometry in any kind of flow domain, right, can be simulated, can be visualized with the help of these two lines, right, equipotential lines and lines of constant stream function, and the combination of this will be forming the flow net, which is very, very, important tool for analyzing the flow, that you have to keep in mind. Okay, so these all things. So as we are having still 9 more minutes, right? If you are having any doubt, you start asking the doubt, or else I will give you some idea, right? Particularly how to solve the simple problems based on this. Yes, your queries please first. Then after we'll go for the numerical problems. Till then, I will add some extra slides in this, so we can have at least one problem, one or two problems on each. Yes. Any queries? As usual, no queries will be coming, so we'll take the first problem. Right? We will see how to do the things. So, like question will be something like that. If psi is equal to 2xy, which will be given for any kind of flow domain, determine the resultant velocity at the point which is given as 2 3 is been asked, and also determine the form of phi. What is the form of phi? Let me start. Solution. We know that u is equal to dou psi y, dou y, and v is equal to minus dou psi y, dou x. This we know formula. And psi is given here. We can just differentiate. So u is equal to dou psi y, dou y is 2x, and v is equal to minus 2 times of y. So at point 2 3, right, we can find u is equal to 4 and v is equal to minus 6. So resultant velocity is equal to under root u square plus v square. You can get the first answer. The first answer is 7 point something. It will be coming 7.21. Just you leave it over here. So this is over. Next one, we need to find out the form of phi. So we have to use d phi. D phi is equal to u dx v dy, that we recently derived, right? So u dx and v dy. So you need to use the value of u and v, which already we calculated over here. So just substitute this value over here. So we can say that this is 2x dx minus 2y dy. Yes or no? Now integrate these terms, right, separately. So we can say that phi is equal to, this will become x square, right? So x square minus y square plus constant. We got this. Yes or no?
Yes, sir.
Now, once you got this, we need to know the value of constant. So how to find that, right? That is called reverse engineering, right? That we need to do. So as phi is equal to x square minus y square plus constant, we say just differentiate this with respect to x, right? Differentiating with respect to x. If you do so, you can say dou phi by dou x is equal to 2x plus dou c divided by dou x. So what is the dou phi by dou x? That is basically u. Yes or no? But for you, you know the value which is given as 2x. Clear no? 2x, just substitute the value over here, 2x. If you put that, so dou c by dou x becomes 0, or you can say dou c is equal to 0, integration. We are not getting anything right, so it is going to be again a constant. So If you do that, you are getting only constant. So constant is a constant. So there is no meaning of it. So directly you can say phi is basically nothing but x square minus y square. Just you leave over here, and there's no meaning of constant. Constant is not going to do any changes. So this is the final form of phi. So this kind of problems may be asked. So this is the one problem which we have solved for the psi, and the same sort of equation may be given for phi, and they will be asking you to calculate the velocity, right, or velocity components at any point, or they may be asking if phi is given, find out the psi. You have to proceed in a similar way, right? Like here you have written the d phi, you write the d psi. If here it is phi, then if you are writing d psi, this will become minus b dx and plus u dy. So you have to remember all these formulas, right, which been given to you. So these all formulas that we have derived over here. This is given for psi, and similarly we have got for phi as well. So as a summary, I will say today we have covered the concept of phi and psi and their interrelationship, and also we have seen numerical applications, right? Simple numerical applications using these functions, right? So I have given you only one example where psi was given and it was asked to find out the resultant velocity, right? As well as it was asked to find out the phi out of psi, and we have seen the process. If we are replacing this psi by phi, then process will be following in a similar step, but slightly difference over here. So if I am putting here phi, then u will become basically dou phi by dou x instead of dou psi by dou y, dou phi by dou x. Whatever is given here, your difference with respect to x, and v will become dou phi by dou y. And finally, when you come here at this point, this will become minus v dx and plus u dy, and procedure will be same. You will get a constant, find out the value of constant, right? Then for put the value of constant back in the equation, and finally you predict that this is the final form of psi. So this I am giving you as homework. You try from your end, right? If we are placing psi by phi, what will the form of you know what do we say, psi, that you do from yourself. So any questions, please respond.
No doubt, sir.
No doubt. So with this, we have basically covered the first segment of the second unit. So we have covered the fluid kinematics, and we have covered even fluid dynamics. And fluid dynamics, we have seen the applications of Bernoulli's theorem in three different forms: orifice meter, venturi meter, and Pétot tube. And we have solved corresponding numerical problems also, right? And my suggestion is now to you, just go through the standard book, right? Go through the solved examples, understand them. If you come across any doubt, please report to me. We can have a discussion on it. Is that clear?
Yes, sir.
Okay, so here I will be closing the today's discussion then. See you all in the next class. Have a nice day. Good day.
Thank you, sir.